Alright, what's up guys? In this video we're going to pick up with a little bit more calculus here, and today we're going to work on another example of using trigonometric substitution to evaluate an integral. So the example that we're going to start with in this video is we're asked to integrate dx over x squared times the square root of x squared minus 64. Okay, so let me just quickly remind you of your trig substitutions, and we'll talk a little bit about it, and we'll get into it. So as I always mention at the beginning of all my trig substitution videos, keep in mind that trig substitutions don't have to be under square roots. You just need to be looking for a specific form. So just because there isn't a square root with that form under there, whether it be a squared minus x squared minus a squared plus x squared plus a squared, because we know addition is commutative, that's what you really should be looking for. So just because you don't see a square root doesn't mean that you can't use a trig substitution in certain cases. But let's just start out with just a general definition of all of them. So now that you know they don't have to be under square roots, but I'll put them under there anyway. So if I see the square root of a squared minus x squared, then that is x is equal to a sine theta. If I see the square root of a squared plus x squared, or x squared plus a squared, because addition is commutative, then x is going to be equal to a tangent theta. And then the last one is, if I see the square root of x squared minus a squared, then x is going to be equal to a secant theta. So those are going to be your trig substitutions. Okay, so just keep those known facts in mind that I mentioned about trig substitution prior to starting. Sorry guys, phone charger failed. Okay, so what's the appropriate substitution here? Well, this is clearly a secant substitution, and so that's what we're going to be doing. So since this is a secant substitution, we know that a here is just going to be 8. So x will be equal to 8 secant theta. We'll find dx, which is the derivative of 8 secant theta. Well, that's just 8 secant theta multiplied by tangent theta, d theta. Now what we'll do is we'll take all of the information that we have here and start plugging our stuff in. So we'll have our integral, and we'll have 8 secant theta times tangent theta on top. And then down here at the bottom, we have to replace our x's with what our x was, which was 8 secant theta. And we'll simplify it and all that stuff shortly. So let's just set it up right quick. So it's just going to be 8 secant theta. Remember, that's being squared, and we're multiplying that by the square root of 8 secant theta squared minus 64. And all of this is being integrated with respect to theta. So if you set it up that way to start, then you're on the right track. Now let's break it up a little bit, and obviously with trig substitutions, or really with any integral, you don't want to try to rush through things. So for the purpose of the video, we're going to do things slowly and in small incremental steps. Okay, so if we start simplifying the stuff under the square root, we'll get 64 secant squared theta minus 64. If we factor out a 64, we would essentially have the square root of 64 multiplied by the square root of secant squared theta minus 1. So we know that this becomes 8 times tangent squared theta, because we know that tangent squared theta is equal to secant squared theta minus 1. If I take the square root of tangent squared theta, I get tangent theta. So this essentially becomes 8 times tangent theta. Now we go back to our integral, and I'm going to plug all the information in and cancel everything out so you can see what happens. So in an actual class, during a quiz or test, wherever you may encounter a trig substitution problem, which will be obviously in Calc 2, but whether it's a quiz or test, you can shorthand a lot of stuff and you don't have to write everything down. I'm just doing that for the purposes of the video, so don't assume you have to write every little thing down that I'm writing down. You can shorthand some stuff in some cases. So I'm just going to put everything back up on top. I understand that there's some simplification that can be done easily, but I'm not going to skip any steps. So down here, we would essentially have 64 secant squared theta. And then this is just going to be, I'm sorry, not minus, but it's going to be multiplied by 8 tangent theta. And remember, all of this is being integrated with respect to theta. So as you can see here, the thetas cancel out. You do need to reduce this down here to 1 over 64, which will be a constant which we're going to pull out. And then the 8s will cancel out, and one of the secants will also cancel out. So essentially what happens is we'll have 1 over 64, which is just a constant, can be pulled out. And then we'll just simply have the antiderivative of 1 over secant theta with respect to theta, or we'll integrate that respect to theta. And obviously this is just 1 over 64. The integral 1 over secant theta is cosine theta. That's a reciprocal identity. And we integrate that with respect to theta. Now, let's go ahead and, much like we do for the U substitutions, we need to get everything back in terms of the original variable that we were working with, which was obviously x, because everything now is in terms of theta. So remember that x was equal to a secant theta. So if x is equal to a secant theta, then that means that secant theta is going to be equal to x over 8. Now, hopefully you remember that secant, hopefully you remember this from your Pythagorean theorem. Remember that secant, is just the hypotenuse all over the adjacent side. And so the best thing to do is to find, or to use Pythagorean theorem. So we'll have a squared plus b squared equals c squared. And so since we know that secant is hypotenuse over adjacent, then that means we'll have a squared plus 8 squared, and that's going to be equal to x squared. And this essentially becomes a squared plus 64 is equal to x squared. And we know that we can subtract 64 from both sides. If we do that, we'll get a squared is equal to x squared minus 64. And to get the value of a, which would be our opposite side, which is the side that we're obviously missing, we take the square root of both sides. And when we do that, we simply get a is going to be equal to the square root of x squared minus 64. Okay, so that's going to be our opposite side that we were missing. And you can demonstrate this by simply drawing a triangle, which we'll do here in just a moment. And this is just going to kind of give you a feel for the whole thing, you know, just having just a general idea of what things look like. So we'll go ahead and draw our right triangle here. We'll, go ahead and set it down and draw it here. And this obviously, we'll have our angle theta. Over here, we'll have our little box to signify to the right triangle. And so obviously our adjacent side will be 8. We needed the opposite side, which we didn't know initially, remember? So that was the square root of x squared minus 64. And the hypotenuse is always going to be the longest side of the triangle, or it's the side of the triangle that's directly across from the right angle. And we know that that side was just obviously x. So if we go back to our integral, we have 1 over 64 times the antiderivative of cosine theta d theta. Now we know if we take the antiderivative of cosine theta with respect to theta, we just simply get sine theta. Now again, this is where the Pythagorean theorem comes in, because remember that sine is opposite over adjacent. So if we take the respective sides, so we have that triangle there, which is a good idea to actually draw it. It's just going to be the square root of x squared minus 64 all over x. And we know that there was a 1 over 64 that was originally outside because it was a constant that we pulled out. So we can go ahead and kind of multiply that through and, write our final answer. So the final answer for this integral using trigonometric substitution. So we have our integral here. We were asked to integrate dx over x squared times the square root of x squared minus 64. And our answer to this integral, I'm just going to write it as the square root of x squared minus 64 all over 64x. And then we'll need to tackle on a plus c to the end, because this is an indefinite integral. And that is how you evaluate this integral using trigonometric substitution. So hopefully that made sense. Okay, so if you guys have any questions about this, let me know. I'm going to post a couple more examples of these so you guys can see them, but this is just a general idea of how to do trig substitution. So let me know if you got any questions further, and I'll answer them. I'll see y'all for the next video.